Alright guys, today we're sketching curves described by parametric equations. So just kind of a summary before we start this lesson. Think of this, we've graphed on an xy axis, we've graphed functions including trigonometric. We've graphed, let's see, vectors, okay. We've graphed polar, right? And now we're going to get into parametric equations. So remember, as you do these problems, you are going to be wanting to go back and forth between using your calculator and not having to depend on your calculator. Okay, so keep that in mind. Alright, as we have seen most recently in section 8.3, there are scores of interesting curves which, when plotted on the xy plane, neither represent y as a function of x nor x as a function of y. In this section, we present a new concept which allows us to use functions to study these kinds of curves. Okay. Imagine a bug crawling across a tabletop starting at point O and tracing out a curve C on the plane as shown below. The curve C does not represent y as a function of x because it fails the vertical line test, right? So it's not a function. And it doesn't represent x as a function of y because it doesn't pass the horizontal line test. However, since the bug can be in only one place, x, y, at any given time, we can define the x coordinate as p as a function of t, and y coordinate as p as a different function of t, not necessarily the same. Because if we're talking about time, right? So this is time, you're still in a certain position over time. Okay? In one position, you're not in two places at once. Okay, so specifically because we're talking about time. Okay, curves described by parametric equations. The function describing the curve C traditionally used f of t to represent x and g of t to represent y. The independent variables of t in this case is called a parameter and the system of equations. So this is what it's going to look like, okay? X represents the function f of t, and y represents the function g of t. It's called a system of parametric equations or parametrization. That's a mouthful. Of the curve C. The parametrization of C endows it with an orientation, so starting point, and the arrows on C indicate the motion of direction of increased value of t. So when we graph, we're going to have to do those arrows too. It is important to note that the curve itself is a set of points and as such is devoid of any orientation. The parametrization determines the orientation, and different parametrizations can determine different orientations. That's a mouthful. Okay, so let's get into what this means, and I'll discuss that as we sketch this out. So of course, with sketching this out, what we want to do is make a table. Okay. We are going to have our t values. We are going to have our x of t, or a function, the first function of t, or the x coordinate. We're going to have the second function of t, which will be our y coordinate. And then we have our x, y that we will be plotting. Okay. Now, keep in mind what we're doing for time. Keep in mind for where we start and if we end, or if it keeps going on forever. Now, I know I keep saying that t is time, and that's technically what we're representing of it. And many of you are probably going, Ms. Heckman, why would we ever start at -2 if t represents time. T doesn't always have to represent time. It represented time in the situation they talked about with the bug. It's just a value. Okay, so in this case, this is the general setting. T doesn't necessarily mean time, and it can't, because we would never have -1 and -2 time. We would never go back in time. Okay, so I'm going to start with -2, and it is at -2. Okay, so it starts at -2. Now when I plug in -2 to the top, I would get 4 minus 3, which is 1. Plug in -2 to the y, and I will get -5. So I have 1 comma -5. Now, because I have a stop or a start in a direction, I'm actually going to start graphing these as I calculate them out. So 1, -5. So 1, 2, 3, 4, 5. Okay, and that's where I start. Now let's go to next. Let's do a friendly value. So let's just keep it at integers. So -1. Now when I plug in -1 to x, I get -2. When I plug in -1 to y, I get -3. So the coordinate I'm looking at is -2, -3. So -2, 1, 2, and then 1, 2, 3. Alright, so this is the other reason why I'm plotting as I go along, because this will connect in somewhat of a curved fashion. Okay, and I'm going to draw an arrow because I went from this point to this point. Okay, we're not going back and forth. Remember, we're going from smallest to greatest. Alright, now let's do another one. Let's do 0. So I get -3, -1. So -3, -1. Okay. -3, -1 is right here. So again, I'm going to curve that up and arrow that out. Now guys, if you wanted to see that it was a curve and not a line, all you gotta do is put like the 1/2 in there, and then you can see how it's curving. Now if it was linear like that, both of these would have been linear, but we should assume that because the top one is a parabola, that it's going to be curved. Alright, let's keep going until we know that there's some sort of pattern, because right now it looks like I'm coming up, but I don't want to stop there just in case. So if I plug in 1, I get -2. If I plug in 1 over here, I get 1. So we have the point -2, 1. -2, 1. So as you can see, it's starting to curve around, and I'm going to put my arrow there. Okay. Okay, let me keep going so I know what this does. Let's put in 2. 2, I get 1, and I get 3. So 1, 3. So I'm coming back around at 1. I'm 1, 2, 3. Okay, very tempting to do linear, so I'm just going to curve it just a little bit. Okay, I want to see what it's doing right here. Let's double check. Let's keep going. So if I do 3, I get 9 minus 3 is 6, and 10. 6 minus 1 is 5. So I'm at 6, 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Alright, now what can we assume? If we kept going up, what's going to happen to this x value in this function, and what's going to happen to this y value in this function? Well, if we look, since we are going positive numbers, this one keeps raising up and this one keeps raising up, so it's going to keep going. We do not have a stopping point because it's just t is greater than or equal to -2. So we just graphed our first parametric equation. Alright, let's look at this one. Okay, so if you look, the x part looks like a cubic. So cubic is your kind of your snake there. And y equals 2t squared. Well, that's a parabola. So we have a bunch of curves going on here. Now the other thing I want you to see is we have a starting and a stopping point. So when we write our table, we really have to keep in mind, what am I doing? This should be x of t and y of t. Okay, of course we're going to have -1 and 1 in there, and an easy number in between is 0. What we might want to do, I know it's going to look sloppy, and I said use easy numbers, but what you might want to do is use the decimals just so I can show you whether there's a curve or not and what direction. Okay, so actually I'm going to put this -1, I'm going to show you the 0 and the 1. We're going to look where it's plotted, but then we're going to put in the in-between just in case. Okay, so when I put -1 in, I get -1, 2. So the coordinate I have is -1, 2. Okay, -1, 2, right here. So it starts right here, and then if I plug in 0, I get 0. Now, usually I will connect those guys, but I wanted to show you a little bit of how it's going to end up. The other thing is I keep going by 1s. You guys could have gone by 2s or 5s or whatever to help analyze what that looks like, so it's not so just in this little spot. And at 1 I get 1, 2. So as you can see, I go back up, and it's very tempting to make this V here, but again, I'm going to actually take my calculator right now and look what happens at -0.5. Okay, so -0.5 cubed, right, because that's what we're doing for x, is -0.125, and then 2 times -0.5 squared equals 0.5. So I'm going negative just a little bit, and I'm right here. That is not linear. As you can see, that is going to curve, an inward curve. Okay, I know it almost looks linear there, and I'll make a different one on the side to make it bigger. And don't forget, I'm starting at -1 and I'm going towards 0, so there should be an arrow there. It happens the same thing on the other side. I get 0.125 and I still get 0.5 on the side. Okay, so it actually curves up into this V. I'm going to make a better graph on the side right now, and this is why I'm saying you might have not wanted to go by 1s. If we started at the -1 and we go down to 0, it makes this curve. And I want to make sure I'm showing my direction. And then it curves back up. Okay, so that is what it's supposed to look like. It's just harder in that smaller spot. Awesome. Alright, now what we're going to do right now is still graph some parametric equations, but we are actually going to do it with other complex equations. Okay, so in example 4, first thing I'm going to do is do my table. So I have t, my x, and my y, and then my x, y. Now, as you guys can see, there is no grade graph because we're going to sketch what it will look like, and we're not going to be perfect, okay? And I want it big enough so that way we can see what's really happening to this graph, okay? What I want you to see is that we have 0 here, and it is included, and then it keeps going on forever, okay? But if you look, oh, actually, I am on the wrong example, guys. Sorry. Okay, there we go. So at 0, if we plug 0 into the t here, I get 2. And then if I plug in 0 to the second one here, I get 1. So that's a nice point. 2, 1. I'm going to go out 1, 2, 1. Alright, now you definitely need your calculator for all this, but we need to be prepared in case we're not using a calculator, right? So how can we plug in a number up here and know what's going on with e in the decimal? Because I don't know about you, but I can't do e to the third in my head. I need a calculator for that. So let's think about it. What values cancel out the e to make them very nice figures? Well, that would be ln. So I'm going to go up to ln2. Now, why didn't I put in ln1? Well, ln1 is 0, so technically we already have ln. Okay. Now, if you remember an ln graph, okay, an ln graph does this. Right, so we want to think about where that spot's going to be, okay? So ln of 2, because this is 1 right here, ln of 2 is right over here, okay? Alright, but let's check. Let's actually do this out, because ln's look very nice in this case. So, if we have 2 negative ln 2, we will come out with the value of 1. Okay. Y, here we go. E to the negative 2 ln 2, we would come up with the value of 1/4. Okay, you want me to do that calculation on the side for you? I will. So, let me do that again. 2e to the negative ln of 2. Okay, remember exponents are in front, so that comes out to 2e ln 2 to the negative 1. I don't know why I put 2. There we go. Because that front becomes an exponent. These two cancel. We have 2 times 2 to the negative 1, which is 2 times 1/2, and that's where we got our value of 1. Now let's do the next one. Again, the y. Okay, I get e to the negative 2 ln of 2. That's the same thing as saying e to the ln of 2 to the negative 2. The e and the ln now cancels. Okay, you cannot cancel it up there. You have to move that coefficient up. We get 2 to the negative 2, which is 1/4. So that is how I'm doing the algebra without a calculator, guys. So we have 1/4. So if I get a 1, I go to 1/4. Wow, I'm getting very low here. Okay, so that means I am starting here and going this way, and I'm going to put my arrow down. So let's try that again. Let's go ln 3. When I do that, of course, I'm going to do these calculations a little bit faster. So I get 2/3 and 1/9. 1/9. 1/9 and 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 1/9 Alright, so I get 2/3, 1/9. So 2/3 is closer than 1. 1/9 though is getting very, very close to 0. So what's going to happen, if you look, guys, it's going to keep getting closer and closer here. Will it ever reach 0? No. Okay? Because it doesn't exist. Think of that. E has an asymptote. Ln has an asymptote. So in our parametric right now, we have an asymptote. And we keep going on in this direction because t is just greater or equal to 0. Starts at 0, go here. It's so weird when I say starts at 0, right? Because it looks like it starts at 1. But remember that t is having our two parts. We have a function for x value and a function for y. Two things are happening at once. Okay. Alright, now let's do one with some trig in it. Okay. A couple things I want you to notice. Cosecant is the inverse of secant, or sine, I mean. Woo, let me say that again. Cosecant is the inverse of sine. So keep that in mind. And then, as you can see, we're going from 0 to pi. If you look, though, it's not equal to. So we have to think about what happens there. Okay, guys? So let me do our t, our x value, y value, and our xy. Alright, so I'm going to include 0 just to see what happens, okay? And when I think of nice values, I want to be able to think of some of the things on the unit circle that would allow me to do sine and cosecant, nice numbers. Sorry guys, I'm trying to focus this. There we go. Alright, so when we do this and we look at sine of 0 is 0, right? But if I were to do the reciprocal of that, and I kept saying inverse, but I meant reciprocal, I would get undefined. Okay, so that doesn't exist, right? We don't have a point there. So what do we do from here? Okay, well, let's look at the unit circle right now. What are nice sine values that when you take the reciprocal, you would get another nice value? Well, if you remember, that's going to be your 1/2, right? Well, where is... Alright, so if we looked at that 1/2, then we would be looking at pi over 6. Okay, so sine of pi over 6 is 1/2. And if we do the reciprocal there, we get 2. So we have a coordinate of 1/2, 2. So I'm going to make one over here. Make these bigger so that way we can see what's going on here. So at 1.5 we're at 2. But really, guys, that's not our starting point now, is it? No, it's not. Because our starting point was actually at 0, very, very close to 0. But I don't know about you, but I don't want to put like major little points to see what happens, okay? So what I want to tell you is that we are actually going to get very, very close to the undefined, or that 0 undefined, right? We know it's 0, so we know it's up here, but we don't know where it is. So it gets really, really close, but it never touches. Now, here's the idea. This arrow right here is not the direction. This arrow is actually where it's starting. It's starting really, really close to 0, all the way up there, but it goes on forever. So that starting point we can't actually get to. Okay, so keep that in mind. That is not direction. When we do our next point, that's where our direction is going. So what's the next nice point for sine? Well, pi over 2 would be pretty nice. So pi over 2, sine of pi over 2 is 1. and the reciprocal of that is 1. So we get 1, comma, 1. Alright, 1, comma, 1 right here. So I'm going to kind of curve this. Of course, this curve looks a little bit different. Okay, and we're going in this direction. Let's keep that in mind. So maybe, in sense, if you want to graph this and keep notes, have these two different colors and then label, okay, this is where it starts and this is the direction it's going. Now, I don't want to go straight to pi. What's our next nice sign value? Excuse me. 5 pi over 6. And we're back to this 1/2, 2. Uh-oh, what do we do? 1/2, 2. That actually means, and this is another reason why I'm going here, we get to this value, but then we change directions and we go back up. Okay? So there's no arrow right here, guys, because it stops there and it changes direction. Think of the bug walking, right? We have no idea where it came from, and then all of a sudden it walks, and then it stops, and it turns back around, okay? Okay, well, let's think of this now, because we're going to pi. There's only so much time in here, right? So if I look at pi, sine is 0. So we're going back towards 0, but here we have undefined. So if you did it in terms of what they were talking about, a bug over time, that bug came out of nowhere, stops at a certain place, and goes right back up to nowhere. Okay? It gets very, very close to 0, but it never gets there. Very hard to draw this one because our arrows kind of overlap, right? Alright, one more. Let's do our table. We have t, x, y, x comma y. Okay, we're going from z to 3 pi over 2, so let's start at our 0. That's a nice starting point right there. So if I put in 0, cosine of 0 is 1. 1 times 3 is 3. 3 plus 1 is 4. Okay, plug in 0. Sine of 0 is 0. 0 times 2 is 0. So we have 4 comma 0. 1, 2, 3, 4. Okay, that is our starting point. It is there. Alright, nice numbers, right? So for cosine and sine, probably just, so we're both nice for both of them, would just be at our 90-degree angles, right? So let's do pi over 2. Cosine pi over 2 is 1. No, is 0. So x value is 1. Sine pi over 2 is 1, so that's 2. So we get the coordinate 1, 2. 1, 2. Okay, now I'm going to curve this, right? Think of our sines and our cosines are curved too. Okay, and we're going in this direction. Now we have pi. Okay, if we plug in pi there, we get -2. Plug in pi for y, we get 0, not for y, but into y. We get -2, 0. So at -2, we're at 0. Okay guys, so now you know how I hesitate right here. So I get -2, 0, correct? But if we look and we plug this point, we get -2, 0 over there. I shouldn't be having this like sharp turn right here like I did before when we were dealing with the cubic and the parabola, but these should be nice curves. So I actually think that I curved this the wrong way. I think we're supposed to go up here and around. And we can double check that, right? We can double check that by actually doing like pi over 3 in there. And we find that, hey, I don't go lower, I actually go a little bit higher here. I'm 1 point something, and here we are. Okay, so be careful on how you're curving, and if you're wondering if you did something wrong, find a point in between. When graphing, you can pick any point you want. It's nice to use nice, quote-unquote, nice points that come out to good, nice integers, but sometimes we need those decimals to figure out which way is it, an undercurve or an overcurve. So let's keep going on this and see what happens. So we have 3 pi over 2, and when we plug 3 pi over 2 in, we get 1 and negative 2. Okay, so if I go to 1 and I go negative 2, I'm down here. And that looks a little bit nicer because, as you can see, we're curving inward. Now, I bet you if this were on a normal graph, this would look more like a, like a circle, almost like this. Now, there's no more arrows at either end because it's actually having a start and a stop position, guys. But what you do need is the direction. Wow, I can't draw your arrows today. In which way, let's say, the example, the bug would move. Alright, so why don't you go and practice some of these curves. Make your table out that makes it clearer. And then if you have to, add some points in between to see which way it's curving.